Hello everyone, today I will present timers and counters. First of all, we will see the purpose of timers and counters. Timers and counters can work either as a timer to generate a time delay or as a counter to count events happening outside the microcontroller. Now we have two timer two two 16-bit timers or counters in microcontroller 8051. Each 16-bit is accessed as two separate registers of lower byte and higher byte. See, this is timer 0. This is TL0 or D0 to D7 of timer 0. This is TH0 or D8 to D15 of timer 0. Similarly, we will call D0 to D7 of timer 1 as TL1 and D8 to D15 of timer 1 as TH1. Now, timer 0 and timer 1 data can be loaded as normal as we load another register. This instruction move TL0, hashtag 4FH shows that 4FH data can be moved into the TL0 register. Similarly, the data of the TL0 register can be moved into the R5 register. Similarly, we have instructions for timer 1. Data 4FH can be moved into TL1 by this instruction move TL1 hashtag 4FH, and the data of TL1 can be moved into the R5 register by this instruction move R5 TL1. Now this hashtag is there because this is microcontroller's way of recognizing that this is an immediate data. Now we will see timer operation. The timer register is incremented every machine cycle, thus working at an increment frequency of 1 by 12 of the oscillator frequency for 12 oscillator machine cycle. Any present value, that is initial count, can be loaded into TH0, TL0, or TH1 or TL1. For example, we have clock frequency as 12 MHz. Therefore, one clock period will be 1 by 12 microsecond. Machine cycle time will be 1 microsecond. Thus, timer register will be incremented every microsecond. If timer is initialized to 00H, maximum count possible can be FFFFH because it is a 16-bit register. So maximum time measured will be 2 to the power 16 microseconds. The FFFFH is 2 to the power 6. As we know that FFFFH is 2 to the power 16, so we multiply 2 to the power 16 into microseconds. That will be equal to 2 2 to the power 6 and 2 to the power 10 microsecond, and that will be 2 to the power 6 millisecond, and you can see the calculation that will be approximately equal to during counter operation. When they work as counter, they will count the external events such as pulse train, so they are incremented by 1 for counting the number of external events. The 000H will be the initial value and maximum possible counting value can be FFFFH. Now, so the capacity of counting the operations will be only FFFFH. Now what happens if the event exceeds the number of FFFFH? Here comes the overflow condition. Overflow condition is the condition in which the maximum value is reached and then it is incremented and it comes back to 00H. It is also called as lower condition. As we can see, it rolls back to 000H. So now this is a problem. How we will account this problem? So for accounting of this problem, there are overflow flag bits in the TCON register. What is TCON register, that we will see in detail later. For now, we will know only that overflow flag bit is set if overflow condition is achieved. Overflow flag bit are provided separately for timer 0 and timer 1. So if in timer 0 overflow condition occurs, overflow flag bit of timer 1 will be set timer 0 will be set. And similarly, if overflow condition in timer 1 is achieved, then overflow flag bit of timer 1 will be set. Now we will see how we can access these in special function registers. So TL0 is accessed with address 8AH in SFR. This is TL0 and this is accessed with 8AH in the special function registers area of the RAM. TH0 similarly TH0 is accessed with address 8CH in the special function register area of the RAM. Similarly TL1 is accessed with the address 8BH in the special function area of the RAM, and TH1 is accessed with 8DH in the special function area of the RAM. Here is the diagram. See, this is 8AH and this is accessed. This is how we can access TL0. This is 8BH. We can access TL1, and at 8CH we can access TH0. 8DH we can access TH1. Now these are not bit addressable. Only 8 bits combinedly can be accessed, and also timer 0 cannot be accessed as a whole, and timer 1 can also not be accessed as a whole, because these are 16 bit registers and we have space as 8 bit registers only. Now we will come to these registers. These are TMOD register and TCON registers. These control the operations of timers and counters. First we will see the TMOD register. TMOD register is also called as timer mode register. It is an 8-bit register, out of which these 4 bits are allocated for timer 1 and these 4 bits are allocated for timer 0. So whatever the function will be of gate in timer 1, same function of gate will be in timer 0, and similar is the case with other bits. Now this is gate, which is used to start or stop the counter timer. This can be done in two ways: using hardware interrupt. Timer is enabled when INTX pin is high and TRX control pin is set. Now this is INTX pin. INTX means X can be 0 or 1. So if the timer is 0, sorry, TRX TRX means if the timer is 0, it will be TR0 for timer 0. If the timer is 1, it will be TR1 for timer 1. So TRX means TR0 or TR1 depending on the case. So we have oscillator. This can be INT0 or INT1. Similarly, this X can be INT1 or INT0. Oscillator frequency is divided by 12, then timer. Then this operation is of timer operation. As we can see that CT bar is 0. CT bar is the TMOD bit which tells us whether the timer or counter operation is happening. Here is the CT bar. There should be bar. So CT bar tells us the whether a timer 1 or timer 0 is act. If this is 1, then it will act as timer 1 will act as counter. If this is 1, then timer 0 will act as counter. Similarly, if this is T0, then timer 1 will act as timer, and if this is 0, then timer 0 will act as timer. So we have when it works as a timer, CT bar is equals to 0, and when it works as counter, CT bar is equals to 1. Now this is the gate bit circuit. This is gate bit in TMOD. When this is equal to 1, this is 0, and when INT bar or INT0 is 1, then this OR gate will have result as 1 that will go in this gate. Now if TR1 or TR0 in bit in TCON will be 1, then this will be 1, and if both will be 1, this will be 1, and timer circuit will start. Now we will explain what is this TR1 or TR0. later when we will see T-con register. For now, we can understand that is T-con register is here we have T-con register. This is TR1. For now, we can know that this TR1 is used for setting or stopping of the timer or counter. Now, I have explained this gate bit and CT bar bit. Now I will explain M1 or M0. These M1 and M0 are mode select bits. There are four possible modes of this timer or counter. First is mode 0, second is mode 1, third is mode 2 and mode 3. So the decimal equivalent of these binary number is the mode. Mode 0 is exactly same like mode 1. Mode 0 is a 13-bit timer or counter. It can count up to 1 when all will be ones in 13. Only 13 bits of the 16-bit register will be used. The maximum count value will be 1 FFFF, 1 triple FH when all the 13-bit registers will be 1. So we will start with initial value of 000H and stop at 1 FFFH. Now this is the figure for timer 0. This we have seen this circuit. Again, I will explain this again. This is gate. If this will be 1, then this will be if this will be 1, then this will be 0. This is INT 0 pin, or we can use as INT 1 pin. This will be 1 for setting the interrupt, and the result of this OR gate will be 1. And if this OR gate will be 1, we have this TR0 for timer 0. It can be T1 for timer 1. This can also be T1. So this is figure for timer 0 and this is mode 0. So if this AND gate will be set, we will have timer operation in this case, or we can have, if this switch is connected to this, we can have counter operations. So in TL0 there will be 8 bits and TH0 there will be 5 bits. This is mistakenly written wrong, and if overflow condition occurs, then TF0 will be set and corresponding interrupt will be generated. Now in our figure, when CT bar is equals to 0, there will be timer operation. Count will increment every cycle provided. The first way is that TR01 or TR1 equal to 1 and gate equal to 0. Another way is TR0 equal to 1 and gate equal to 1, or these two can be 1 and INT bar or INT 1 equal to 1. Thus, by sending logic high signal on INT 0 bar or INT 1 pins, timer 0 or timer 1 can be started. This can be used for finding pulse width in the following way. Source of flat pulse is connected to INT 0 or INTR when this is the gate equal to 1 and TR0 or TR1 equal to 1. The pulse curve goes to highest timer starts counting at the 1 by 12 clock frequency. When pulse goes low, timer stop. So in this way we can calculate the pulse width. See here, this is when the timer starts and this is where timer the stop. Now timer will count as 1 by 12 of the clock frequency. So we can calculate the timer width in that way. ISR can read the timer value and ISR can store the time. ISR is the interrupt service routine and this timer value can be processed as required by its application. Now mode 1 is 16-bit timer. It can go maximum of it is same as 0-bit. 13-bit timer it can go maximum same but the fact is it can goes maximum up to FFFFH, and then if it goes more than FFFFH, overflow condition will occur and TF0 or TF1 will be set. TF0 will be set for time if overflow occurs in timer 0. TF1 will be set if overflow occurs in timer 1. Here is the circuit of mode 1, which is 16-bit counter. Of TH0 all the 8 bits are used. Of TL0 all the 8 bits are used, and hence if overflow is occurred, TF0 is set to 1 and corresponding interrupt will be generated. This will be same as the mode 0. This is for timer 0s. Similarly it can be for timer 1 also when this is TR1 and this is TR0, and this is TH1 and this is TL1 and this is TF1. Mode 2 is auto reload mode. It is an 8-bit timer mode. The value is first loaded in the TH register, then it is copied into TL register, and then values are increased. Now when the overflow condition is occurred, the initial value is again reset into the TL0. First the initial value is loaded into the TH0, then it is loaded into the TL0, and when the TL0 reaches its maximum capability, the TL0 again reloads the value of TH0 into TL0. In this way, this is called auto reload mode. We have explained this circuit before also, so I will not explain in this. Mode 3 is slate timer mode. For timer 0, timer and timer 1 may be programmed in mode 0, 1 and 2 independently of similar mode for other timer. This is not true from mode 3. Timers do not operate independently if mode 3 is chosen. Placing timer 1 in mode 3 causes it to stop counting. The control bit TR1 and the timer are then used by timer 0. So here is the circuit of timers mode 3, and here we can see TR1 and TF1 are used by TL0. Well, means timer 0 only uses the TR1 and TF1, and timer 1 cannot count in this mode, cannot work in this mode. Now we will see the TCON register. It is a timer control register. It is an 8-bit register. It controls whether the timer or counter is started or stopped. So this instruction is used for starting the timer. Set BTR0 for timer 0, set BTR1 for timer 1 to stop the counter by using these two instructions. CLR TR0 for timer 0 and CLR TR1 for timer 1. Now why we need to stop the counter? Because overflow condition can occur, and to avoid the overflow condition we have to stop the counter before it occurs, before it reaches the FFFFH. If overflow is achieved for timer 0, TF0 is set. For timer 1, TF1 is set. Now I will show the diagram. TF1, this is TF1 for overflow flag bit of timer 1. This is TR1, which is which is timer 1, which shows that timer 1 is started or not. This is TR0, which shows that timer 0 is started or not. This is TF0, which shows that overflow occurs in timer 0 or not. So if this is set means overflow occurs. If this is set means timer 1 is operating. Overflow occurs in timer 1. If this is set, then it means overflow occurs in timer 0. If this is set, means timer 0 is operating. These upper nibbles are used for timer operations and these lower nibbles are used for interrupt operations.